Mr. Drew, welcome to part 2 of our introduction to finding derivatives using the chain rule. Examples like this where we have f of x is equal to 3 times the cosecant of x squared. Now this is part 2. In part 1, where you'll find a link in the description below, we discussed the introduction of the finding derivatives using the chain rule and how it is a composition of functions. So we know the power rule, the derivative using the power rule, which we're now going to call the general power rule. And indeed, every one of our derivative rules now are going to be sort of a general derivative rule. We talked about in the previous sections finding the derivative of two functions multiplied together, two functions divided together, and the chain rule comes into play when you have a composition of functions, a function inside of another. Now, though this is part 2, I'm not going to be spending as much time introducing the notation. I'll make sure to highlight that composition of functions as we go. In case you missed part 1, you're not going to be totally lost. So we have the derivative with respect to x of the sine of u, right? So we have an expression that is inside of our math function that's not a perfect match to just the sort of variable with which we're taking a derivative with respect to. So this might be just literally the variable u instead of variable x, or just another expression. So we have the derivative with respect of x of the sine of u is equal to the cosine of u times u prime. You can kind of see here what's going on when we have a composition of functions, a function inside of another function. We take the derivative of the outside first, the derivative of sine is cosine. And that's it, just the one thing, just the one math operation. Then we multiply out after that the derivative of the inside function with respect to x. That u prime is a du over dx. The derivative of cosine of u is equal to the opposite of the sine of u times u prime. The derivative with respect to x of tangent of u is equal to secant squared of u times u prime. The derivative of cosecant of u is equal to negative cosecant of u cotangent of u times u prime. The derivative of secant of u is secant u tangent u times u prime. And the derivative of cotangent of u is equal to negative cosecant squared of u times u prime. In a previous lesson, we derived one or two of these rules for trigonometry. The derivative of sine is equal to cosine. If you really want to understand what's going on there, you look at the graph of sine and cosine together. Same thing with the cosine, but the tangents, cosecant, secant, and cotangent, these last four rules, if you forget them, you don't have to be lost. You just have to rederive these formulas using the quotient rule for finding a derivative. And the second thing I want to mention is we have sine and we have cosine. We have tangent and we have cotangent. And we have secant and we have cosecant. Now, it's not like the derivative of sine and cosine are identical, but there's something to pay attention to. And there's some kind of relationship between trig functions and their cofunctions. In this case, all of the cofunctions have a negative in front of the sort of answer, if you will, instead of just the derivative of sine is the same positive sine. The derivative of sine is cosine of u prime. When you're taking the derivative of cosine, you change the sign. It's negative sine, and so on. So just another little relationship we have there between a function, a trig function, and its cofunction. For example, number 1, the function f of x is equal to 3 times cosecant squared of x. Now, one thing that textbooks don't do, and it really annoys me, is they never wrap the expression representing an angle measure that's going into the trig function. They never wrap that in a set of parentheses. It's a really good habit to help keep things clear as you're taking the derivative. What is the composition of functions? It's also kind of interesting that if we say, a squared, anything other than trig, the exponent always shows up in the upper right-hand corner. But when we're talking about trig functions, we kind of put the exponent in the middle of the expression, which can make it a little bit complicated on when you're starting to learn how to take derivatives using the chain rule. And you need to find that composition of functions. So we're going to take a little extra step here, and we're going to rewrite this power of 2 being applied to the cosecant function a little bit differently. We're going to write, and let me get some colors out here. I think the Hopefully the blue and the white will show up well together in the video. We have f of x is equal to 3. Now I'm going to wrap the cosine function, cosecant function, in a set of parentheses and try and highlight that it's the power of 2. The power of 2 is being applied to all of the cosecant of x. What's good about this? As we talked about in part 1, when you're taking derivatives using the chain rule, you work with the outer function first and work your way in, like you saw with that green board with the rules for the derivative rules for the trig functions. So as you look at this, what is the outermost function? The outermost function is something, the something of cosecant squared being raised to a second power. The stuff on the inside, that something is the cosecant of x. So this cosecant of x is our u. When we go to the first line and we go to write f prime and start the process of finding the derivative, we are going to first be doing the derivative using the power rule. It's just something raised to a power of 2. I'm not even going to pay attention to the fact that there's cosecant inside that parentheses. So f prime of x is equal to 3 times something squared. So we're going to bring that power of 2 down, multiply it to the 3, and reduce the power by 1. So we have 3 times 2 is 6. I'm going to keep writing what's inside here in blue to kind of, again, identify or really highlight, try to highlight that composition of the functions. We're going to reduce that power by 1. And you don't need to really write the exponent of 1. All I've done so far is the power rule for derivatives. Bring the power down, reduce the power by 1. Now I'm not going to do 2 or 3 steps at once, but I'm going to write down what I have to do in the next step, which is to finish that u prime, right? That we're going to be taking the derivative then of the inside function. We're going to be taking the derivative with respect to x of cosecant of x. Now, as we go to look at taking the derivative of cosecant of x, the independent variable, or the expression that's inside the cosecant function, is an exact match to that d of x. So in line 1, all we've done is the power rule. We bring the power down, multiplied, and reduced it by 1. So the continuation here is that, of course, we have our good 6 times the cosecant of x. And now we're going to take the derivative of cosecant. I'm going to show the chain rule where we're going to multiply by the derivative of the inside function too, just to let you see hopefully what's going on. The derivative of cosecant of x with respect to x is negative cosecant of x times cotangent of x. And what if we thought that there was another composition? What if we saw that x, we're identifying composition of functions, and we just take that extra step of chain rule, not too far, but we go, okay, we took the derivative of cosecant, got cosecant, negative cosecant, cotangent, and now we're going to multiply by the derivative with respect to x of the expression that's inside the cosecant function. Well, if you write the derivative with respect to x of x, you kind of really just have a dx over dx, which is going to be equal to 1. They kind of sort of cancel out, if you will. Or the derivative of x with respect to x is 1. You bring the power down, you reduce by 1. It's 1. So we have here as our final answer, f prime of x is equal to negative 1 times 6 is negative 6. Cosecant of x times cosecant of x. I'm going to go ahead and put that cosecant squared where we're traditionally used to seeing it. Cosecant squared of x. Wrap that up in parentheses. I just said that bothered me that textbooks didn't do that. And then times the cotangent of x. And that is the end of our first example. Second example coming up right now. For example number 2, we've got g of x is equal to 5 times secant squared of 4x squared. Okay, so again, you don't have to, But especially for teaching this concept, I find it much, much easier to rewrite the power that is applied to the trig function. So we're going to, like the previous one, and it's always a good idea maybe to pause the video and work these problems ahead of time when you see the examples, and then watch me work through it. You know, once you think you know what's going on, give yourself some practice. Okay, so this is, I'm bringing this up and I'm picking some of the, you know, if you want to call them obscure, the slightly less common trig functions that we work with. Bringing that power of 2 that's applied to secant out and maybe wrapping that entire base to really make it easier to identify that composition of functions. The 5 does not have the power of 2 applied to it. That's going to be our constant coefficient that we can pull in front of the derivative notation. And look for that biggest set of parentheses. Look for the math, and it might even be a math function. It might be a big old square root symbol. Look for that biggest grouping symbol and find the function. So what I'm seeing here is 5 times something, like the previous example, something being raised to a second power. So this secant of 4x squared is all inside the power of 2. All of secant of 4x squared is inside the power of 2. Now that I've seen the composition of this orange function inside the power of 2, do we just now have a secant of x, or do you see another composition in there? It's a secant function. Is it just secant of x, or is it secant of, oh, there's kind of a lot of stuff going on. It's not just an x that we're putting into secant or a single variable. It is a 4x squared. It's a whole like expression, if you will. So secant of 4x squared. So we have a outer power or function which is a power of 2. Then inside that we have a secant function, which inside that we have a 4x squared. So there's basically, like, hopefully it's showing up here good, we have blue, orange, and white. We have 3 colors identified in our problem. So we're going to have to work through the chain rule in 2 steps, which I strongly suggest when you're first learning this concept, because it can get a little confusing. So we have g prime of x is equal to, I'm going to pull this 5 out front. It's just a constant multiple, a coefficient, if you will. So it's 5 times the derivative. I'm not even going to take a derivative, I'm just going to copy. The derivative with respect to x of the secant of 4x squared, all raised to the second power. Should have grabbed all my colored chalk. Okay, so we're going to take the derivative of the outermost math function, which is not the secant, not the 4x squared. The outermost function is the power of 2. So our first step is nothing more than, we're not taking derivative of secant, we're not taking the derivative of 4x squared, we're taking the derivative of something to the power of 2. We're using the general power rule. The power of 2 is going to come down, we're going to reduce it by 1. So we have g prime of x is equal to 5 times, bring the 2 down, parentheses, secant. At this point I'm just copying what was inside that power of 2, so let me get the orange back out. 2 times the secant of, where's the blue at, 4x squared, and that power where the 2 was got reduced to a power of 1, so we've just brought the power down, reduced by 1. I'm not going to do another math operation, but I'm going to show what I'm going to do in the next step. What I have to do in the next step is I have to take the derivative with respect to x of the function that was inside the power of 2. So we're going to take the derivative of the secant. We're going to be really just taking the derivative of the secant function, but it's a derivative of the secant of 4x squared. Okay, so be clear here. All I've done to get from the second line to the third line, if you will, or maybe it's my third and fourth line, but all I've done is the power rule. 2 down, reduced by 1. Next, I'm going to take the derivative of what was in the power of 2. The derivative of secant is secant tangent. But I'm going to be copying that, that expression that's inside the secant. So now I'm going to go to white as I kind of work my way down here. So we have 10 secant 4x squared. Okay, grab the orange. The derivative of secant of u is secant of u times tangent of u. So it's going to be the secant of 4x squared tangent of 4x squared. So be clear, we just took the derivative of secant. Now we're going to show what we're going to do in the next step, which is take the derivative of what was in the secant function. We're going to take the derivative of 4x squared, which, like I did with the 5, you can let the 4 kind of move out in front of the d over dx, the derivative with respect to x, and we're really just taking the derivative of x squared. So we have 10 times the secant of 4x squared. Once you get the hang of these chain rule problems, they go very quickly. Let's see here. We have secant of 4x squared times secant of 4x squared, which is secant squared of 4x squared. We've got the tangent of 4x squared. And then the derivative of 4x squared with respect to x is going to be 8x. So our final answer is g prime of x. 10 times 8 is 80. I'm going to have to double check this. I'm not sure if I remember a number being that big. 80x times secant squared of 4x squared times the tangent of 4x squared. And if I've done everything correct, that is the end of our second example. We had that outer function of power of 2, so we use the power rule first. Then we showed that we were going to next take the derivative of what was inside that power. We took the derivative of secant. The derivative of secant is secant tangent of u prime. We only did that. Then we showed that in the next step we were going to take the derivative of what was inside the secant function, which gave us an 8x. And finally, our final answer. So if you have a function within a function within a function, if you have sort of like, that means you're going to walk through that process of the chain rule twice. Let me check my work, and we'll get on to example number 3 right now. Example number 3. We're going to be taking this function g of x is equal to the tangent of 2x. Looks like a pretty simple function we got going on here. And we're going to evaluate the second derivative at the point pi over 6 square root of 3. I'll tell you right now, the reason why they're asking you to evaluate the second derivative is because at this entire point of pi over 6 square root of 3, they're giving you an x and y coordinate because sometimes, and it won't be really till we introduce implicit differentiation, which is right around the corner, sometimes derivatives do ask for both an independent and dependent value, or x and y if those are the variables you're using. So let's get started. We have g of x is equal to the tangent of 2x, so g prime of x. You really shouldn't start to take derivatives that involve the chain rule until you've identified, either mentally or actually writing it out when we first learn about this new concept, you want to identify those that it is a composition of functions. And we do have that 2x that is inside the tangent function. So as I go to write the derivative, we're only going to be taking the derivative of tangent first, not tangent and 2x at the same time. So the derivative of tangent of u with respect to x is secant squared u. So the derivative of tangent is secant squared of 2x. And now we're going to show that, oh, I just took the derivative of the outside function. Now I'm going to take the derivative of the inside function, which you certainly can do all at once if you're comfortable with it, but we're just seeing this for the first time. So we're going to take the derivative of the inside function next. So we first took the derivative of tangent, got secant squared, only that step. Now in the next step, we're going to take the derivative of the function that was in tangent. So we're going to take the derivative of 2x with respect to x, which of course is 2. So g prime of x is equal to 2 secant squared of 2x. Okay. Well, now we're kind of seeing the difference between like example 1 and example 2, because now we have to take the derivative again. But it's 2 times secant of 2x, all of that being raised to a second power. So for the purpose of saving some space, I'm going to erase that power of 2. I'm going to put it outside. And inside that power of 2, we have a secant function. And inside that secant function is an expression of 2x, very similar to the previous problem, not exactly. So let's go ahead and maybe pause the video and try this on your own. We're going to have g double prime is equal to 2 times 2 is equal to 4. We're going to reduce that power by 1, so it's going to be 4 times something to the first instead of 2 times something squared, power of 2. Inside that we have the secant of something. It's the secant of 2x. So in that one step, we just did power. Now we're going to indicate what we're going to do in the next step, which is the derivative with respect to x of the secant. And it's not just the secant of x, it's the secant of something, secant of 2x. And we have the derivative. Man, I really picked one that was just like the last one, didn't I? The derivative of secant is secant tangent. So we have 4 secant of 2x times the secant of 2x tangent of 2x. And now that's all we've done. We've taken the derivative of secant. We're going to take the derivative with respect to x of what's inside secant, which is 2x, which of course is going to be just simply 2. So we have g double prime is equal to 4 times 2 is 8. And I'm saying 2, just 2, because the derivative of 2x with respect to x is just 2. So we have 8 secant of 2x squared tangent of 2x, and we want to evaluate the second derivative at the point of pi over 6 square root of 3. But our second derivative is only asking for the independent value, or the value of x, the value of pi over 6. So g double prime of pi over 6 is equal to 8 times the secant of pi over, now 2 times pi over 6 is pi over 3 squared times the tangent of pi over 3. There was very little simplification in this problem to go from the expanded version of g double prime to our simplified function, or simplified second derivative, g double prime. Be aware that I was not asked for the second derivative. I was asked to evaluate the second derivative. In other words, give a singular number as an answer. Evaluate the second derivative at the point pi over 6 square root of 3. If there had been a tremendous amount, or potentially a lot of simplification that needed to be done, like maybe you're dealing with rational exponents where some of them are negative, and you think about, oh, finding all that common denominator with square roots or something like that. As soon as you get the second derivative completed, which I'm pointing here, but we hadn't technically taken the derivative of 2x yet. Once you get the second derivative completed, you don't need to simplify. We're not being asked for a function. We're being asked for a numerical value. Go ahead and plug that pi over 6 in and get the number, get the slope, or if you will, or the value of the second derivative at that point. So we're looking at 8 The secant of pi over 3, well, at pi over 3 are 60 degrees, even though we never really use degrees in calculus. The cosine of pi over 3 radians is 1/2, and secant and cosine are reciprocal, so we're looking at 2 squared, in case you need a little review of unit circle. At pi over 6, the tangent function, the y value is square root of 3 over 2. Yes, and the x value is 1/2, so the tangent of pi over 3 is going to be the square root of 3. So we're looking at 2 squared is 4, times 8 is 32 square root of 3, and that is the end of my last example. I'm Mr. True. Bam! Go to your homework.